Chapter 7 in our textbook deals with periodic properties of the elements. These properties tend to increase or decrease as we go across a period and down a group. The term periodic, even when we're speaking of the periodic table, suggests that there is some type of repeating behavior. A magazine or a newspaper is called a periodical because it comes out in regular intervals. Every Monday, you get the newest issue of your magazine. Every day, you get a new edition of the newspaper. So there's this repeating behavior that occurs in these intervals or these periods that speak to a repeating behavior. And there are certain properties that we're going to speak of that show that type of behavior as we traverse the periodic table. First, I guess we need to take a look at the periodic table and get an understanding of how the periodic table is organized. It took the work of many scientists over several years to develop a system for organizing the elements effectively. People like John Newlands and Johann Dobereiner put forth ideas about grouping the elements in groups of threes or groups of 8. But it wasn't until Dmitry Mendeleev in 1869, a Russian scientist, put together a periodic table organized based on the atomic masses of the elements. Now, these masses were not concrete. These masses were actually relative masses. German scientist Lothar Meyer independently came to the same conclusion as to how the elements should be grouped. The key difference in Mendeleev's treatment and Lothar Meyer's treatment is that Mendeleev used his periodic table as a predictive tool. He recognized that at the time there were only 63 elements that had been discovered, but he knew that there were things yet to be discovered. And so he left blank spaces on his periodic table in order to accommodate those ultimately soon to be discovered elements, and some instances not so soon to be discovered. For example, germanium, element number 32 on the periodic table, had yet to be discovered. But element number 14, silicon, had. We recognized that elements in the same vertical column tended to have similar properties. So having left a space on his periodic table for what would ultimately be called germanium, he was able to predict the properties. Now, he dubbed it ekasilicon, eka from the Sanskrit meaning first. So the first element beyond silicon would have these properties. It would have an atomic weight of approximately 72. It would have a density of 5.5. It would have a high melting point, and it would be gray in color. Well, when we finally did see the discovery of germanium 15 years later, we saw that many and more of those predictions held true. And Mendeleev's organization wasn't perfect. I mentioned that he based his table based on atomic masses. That was the most fundamental property known at the time. We didn't know anything about protons and neutrons. So understanding the nuclear nature of an atom didn't come along until about 35 years later, with discovery made by Ernest Rutherford. British chemist Henry Moseley went one step further by developing the concept of atomic number, a number that we now know to reflect the number of protons inside the nucleus of an atom. And it is now the atomic number that is the basis for periodic properties. So in this chapter, some of the properties that we are going to speak to with regards of their periodicity are the size of atoms, the ionization energy, uh, property known as electron affinity, as well as a few other properties worth mentioning. Now, in order to have this discussion, we're going to first begin with a discussion of effective nuclear charge. In the last chapter, we learned of valence electrons, those outermost electrons found in the highest numerical energy level in the s and p orbitals that contribute appreciably to chemical interactions. Well, many of these properties that we're going to speak of depend on the interactions between the valence electrons and the nucleus of an atom. It turns out that electrons are attracted to the nucleus in that electrons are negatively charged and protons are positively charged, and protons are found inside the nucleus. But these electrons are also repelled by other electrons. So an electron in an atom experiences both repulsive forces and attractive forces. In short, the concept of effective nuclear charge speaks to the amount of positive charge that an electron experiences, the attraction between the negatively charged electron and the nucleus, which could have more than one proton in it. But each electron doesn't necessarily feel the full pull of the nucleus. Because if there are other electrons that are repelling, other electrons that are shielding the nucleus from a particular electron, then we're not going to see a full nuclear charge being experienced by an electron. The effective nuclear charge can be calculated by taking the atomic number of the element and subtracting a screening constant, a value that is calculated based on the number of electrons that are essentially shielding the nucleus from a particular electron. It should be mentioned that as the basis of other periodic trends, we note that it itself has a periodicity about it. Effective nuclear charge essentially increases as we go from left to right across a period, and it increases slightly as we go down a group. If we want to talk about the size of an atom, we have to understand that when we typically think of size, then we have well-defined boundaries. I want you to think about the room that you're currently in. If I were to ask you about the size of that room, then you would probably measure from one wall to the other, because that is what defines the size, are the walls. Well, in an atom's walls aren't very well defined. If protons and neutrons are found inside the nucleus and electrons are found outside the nucleus, and these electrons are in constant motion, then it would seem that the outer wall of an atom is in constant motion. So thinking about the size of an atom itself is going to involve a little bit of hand waving, a little bit of thinking of things in a different manner. Instead of thinking about the size of an atom by itself, we take two atoms and combine them, whether it be through bonding or a shear collision, and we look at the distance between the two nuclei. Now, in the case of a collision, it's simply going to reflect the distance between the two nuclei as they bounce off one another like hard spheres. But if there is bonding taking place, if we do have two atoms bonded together, the understanding is that the two nuclei are going to repel one another. The electrons are going to be attracted to each nucleus. and the electrons are going to repel one another. It's only when we establish a balance between the nuclear repulsions, the electron repulsions, and the electron nuclear attractions that we see bonding take place. Once that has taken place, we can take a look at the distance between the two nuclei and treat that as the diameter of a sphere, which is essentially the size of the atom. If we take 1/2 of that diameter, then we come up with a radius. And when we typically refer to the size of an atom, the term that we use is atomic radius. The general trend that exists across the periodic table and down the periodic table with respect to atomic radius goes as follows. As we go from left to right across a period, we tend to see a decrease in atomic radius. That means that helium is slightly smaller than hydrogen. That means that nitrogen is slightly smaller than carbon, which is slightly smaller than boron. This can be explained away in that those outermost electrons are feeling a greater effective nuclear charge. So in nitrogen, the 7 electrons in an atom of nitrogen are going to be pulled closer to the nucleus than the 6 electrons in carbon, because those 7 electrons are essentially seeing a larger nuclear charge. Now, as we go down the periodic table, we tend to see an increase in atomic radius. And that's because the number of energy levels increases as you go from top to bottom. So if we look at an atom of sodium, the outermost electrons are found in the 3rd energy level. If you go down to potassium, the outermost electrons are found in a 4th energy level, typically farther away from the nucleus. Now, when we speak of the size of ions, that is a property that is determined by the interatomic distances in ionic compounds. So if we take an atom of sodium and an atom of chlorine, sodium is going to lose an electron, chlorine is going to gain that electron. So if we look at the distance between the two nuclei in the attraction that is a sodium chloride interaction, that's where we obtain the size of ions. And ionic size depends on several factors. Number one, the number of electrons gained or lost, the nuclear charge, as well as the orbitals in which the electrons reside. Cations are formed when electrons are removed from an atom, positively charged ions. Well, cations tend to be smaller than the parent atoms that birthed them. When you remove an electron from the outermost level, then the repulsions, those shieldings between electrons, tend to be reduced. In the case of anions are typically larger than their parent atoms. You're adding more electrons, and those repulsions between electrons tend to increase. Well, that spoke of comparing atoms to their ions. Now we're going to speak of ions compared to other ions of similar electronic structure. The term isoelectronic means having the same number of electrons. We're soon going to find that when entering into chemical combination, atoms do so in an attempt to look like the nearest noble gas from an electronic standpoint. It's a rule that ultimately we're going to call the octet rule. So let's take, for example, neon. Neon at element number 10. Several of the ions on the high atomic number side and the low atomic number side of neon, when entering into chemical combination ionically, are going to gain or lose electrons until they reach 10 total electrons. Oxygen will gain 2 electrons in order to obtain that configuration. Fluorine will gain 1 electron. Sodium at element number 11 will lose 1 electron. Magnesium will lose 2 electrons. Aluminum will lose 3 electrons. We note the size of the ions based on what we saw on the previous slide. Anions tend to get larger as you add electrons. Cations tend to get smaller. When speaking of removing electrons from an atom in order to form a cation, the concept of ionization energy must be explored. The term ionization energy refers to the amount of energy required to remove an electron from the ground state of a gas phase atom or ion. The first ionization energy is the amount of energy required to remove a single electron from an atom. In doing so, you form an ion that carries a charge of +1. The second ionization energy is the energy required to remove an electron from that ion. The third ionization energy, the fourth ionization energy, and so forth and so on. Now, the higher the ionization energy, the more difficult it is to remove an electron. It's going to take energy to remove an electron regardless, but some atoms require more energy to remove that first electron than others. In going from the first ionization energy to the second ionization energy, to the third, to the fourth, to the fifth, we will see that it takes more energy to remove each additional electron. If you want to think about it like this, if you remove 1 electron from an atom, the remaining electrons are not shielded by that electron, and so now they experience a greater nuclear charge. So in order to remove a second electron, it's going to require more energy. The remaining electrons will hold to that nucleus even tighter, so removing a third electron is going to require more energy still. At the bottom of our sheet here, we see the ionization energies of a series of elements in period 3, going from sodium all the way to argon. Not only do we see the first ionization energies compared, but we see the ionization energies of removing successive electrons as well. And in general, I think that we can note a particular trend. Generally speaking, the ionization energy increases as you go from left to right. In other words, it is easier to remove an electron from an atom of sodium than to remove an electron from an atom of magnesium. The ionization energy typically decreases as we go down a group. It is easier to remove an electron from an atom of potassium than it is from an atom of sodium. If we think about the potassium ion, which is farther away from the nucleus, it would be easier to pull that electron away than it would be to pull an electron in sodium, where that electron is closer to the nucleus. And as we go down the periodic table, we see a decrease in ionization energy reflected in the reactivity of these ions. Now, it should be noted that the S&P blocks show a fairly wide range of values for ionization energy. The D block and the F blocks don't change as dramatically. Smaller atoms tend to have high ionization energy values. Hydrogen has an ionization energy value that is significantly larger than that of lithium. And these values for ionization energy are dependent upon a few factors, one of which is effective nuclear charge, how much of the nucleus an electron experiences, and the distance between the electron in question that is to be removed and the nucleus itself. As with all trends and tendencies, we find irregularities and hiccups along the way. Now, this particular trend in ionization energy does not hold true when the valence electron in question is entering into a new sublevel, or when it's the first electron to pair up in a series of degenerate orbitals. So as we go from left to right, we do see a trend in ionization energy. But when you start to take Hund's rule into consideration, when you start to go to a new sublevel, in other words, going from the 2s to the 2p, then we see hiccups along the way. It's important to consider these periodic trends with regards to the energy associated with forming ions, whether they be cations or anions. The ionization energy speaks to the formation of cations, where we are removing an electron. And cations are indeed formed by the removal of valence electrons, those electrons from the highest numerical energy level in the s and p orbitals. The lithium cation that commonly forms is the result of an atom of lithium losing the one electron in the 2s orbital. The calcium cation that forms carries a charge of +2, resulting from the loss of 2 electrons from the 4s orbital. And when we consider our transition metals, we find in many instances that they can form ions of multiple charges. It's because a different number of electrons can be removed and result in a stable ionic configuration. The iron cation that commonly forms in the form of the +2 cation involves the removal of 2 electrons. Well, those 2 electrons come from the 4s orbital. If you write down the electron configuration of iron, it ends with a 4s2 and a 3d6. While the 3d6 electrons are of higher energy, the 4s electrons are the ones that are removed. When removing electrons to form an ion, we remove the valence electrons first. In the formation of an anion, we see an atom gaining one or more electrons. In an anionic formation, we see a nonmetal atom gaining electrons to obtain the electron configuration of the nearest noble gas. So an atom of iron will lose 2 electrons to form a cation, but an atom of oxygen will gain 2 electrons to form an anion. An atom of sulfur will similarly gain 2 electrons to form an anion. An atom of chlorine or fluorine or bromine or iodine will gain 1 electron to look like the nearest noble gas. And the energy associated with gaining an electron is going to be treated slightly differently because of the endothermicity/exothermicity of these processes. Electron affinity is the energy change associated with adding an electron to a gas phase atom. So from ionization energy, we see the formation of a cation. From electron affinity, we see the formation of an anion. But here's the fundamental difference. Ionization energy is endothermic. It requires energy to remove an electron. Electron affinity is typically an exothermic process. By adding an electron, you tend to see the release of energy. And some atoms release more energy than others upon obtaining that electron. Now, as we go from top to bottom, we don't tend to see a great degree of change in electron affinity. As we go across a period, though, it does tend to increase. Now, I need you to understand what I mean by increase. If a process is exothermic, that means that it gives off energy. So in becoming more exothermic, we see that the electron affinity tends to increase. Now, an exothermic value, energetically speaking, tends to be negative. The convention is that energy required is positive, energy released is negative. So when you look at the table listed on the right-hand side, you will see values that are more negative as you get farther to the right. Things like fluorine, chlorine, bromine, iodine will benefit immensely from gaining one electron. So there's a huge energy benefit in the formation of an anion from one of those halogens. Now you will note that the noble gases, helium, neon, argon, krypton, xenon, have an electron affinity that is greater than zero, that is positive. Well, the reasoning behind that is they already have a stable electronic configuration. They do not tend to participate in chemical interactions. They are electronically happy. So in order to add an electron, you're going to have to put it into a new energy level, and that is going to require energy. The last trend that I would like to speak of deals with metallic behavior or metallic character. Now, in a very general sense, we can easily predict a trend based on the zigzag line. On the left-hand side of the zigzag line, we find metals. On the right-hand side of the zigzag line, we find nonmetals. So I want you to consider group 15, the group that includes elements like nitrogen and phosphorus and arsenic and antimony and bismuth and moscovium. As we go from top to bottom, we find ourselves crossing the zigzag line, going from a non-metallic area to a metallic area. So it would be easy for us to draw the conclusion that as we go from top to bottom, we see an increase in metallic character or metallic behavior. I now want you to look at period 4, the period from left to right that begins with potassium and calcium and ends with bromine and krypton. This period traverses the zigzag line from left to right. We start off with metals and we end up with nonmetals. So it would be easy for us to assume that as we go from left to right, we would see a decrease in metallic character. That potassium is more metallic than calcium, which is more metallic than scandium, and so forth and so on. But to speak of this, we kind of need an understanding as to what defines metallic character. What makes a metal a metal? Well, some may be thinking, well, a metal is shiny. Shininess, luster, perhaps that is the defining characteristic of a metal. Well, while many metals do have luster, do exhibit luster, iodine, a nonmetal, element number 53, is a solid at room temperature, and it is quite shiny. It is quite lustrous. So luster while it is a characteristic of many metals, is not the defining characteristic. Malleability, being able to shape or bend, that's not a defining characteristics for metals either. While many metals do show a high level of malleability, of ductility, there are several metals that are quite brittle. Rather than go on and on and on and put you through the ringer with regards of all the things that aren't the defining characteristic, let me cut to the chase. The defining characteristic behind metallic behavior is three-dimensional electrical conductivity. Carbon, as a nonmetal, will conduct electricity in two dimensions in the form of graphite, but it will not conduct in three dimensions. If we compare the conductivities of all of the elements, the nonmetal with the highest conductivity is orders of magnitude less conductive than the metal with the lowest conductivity. So three-dimensional electrical conductivity is the defining characteristic behind metallic behavior. And as we increase in metallic character when going from top to bottom or going from right to left, then we will see an increase in general in conductivity. Thank you for your time. Once again, have a great day.